Alright, so starting with number 10 here. And we have a volcano shoots out blobs of molten lava called lava bombs from its summit as shown. Geologists during eruption use a stopwatch to time the fly of a lava bomb to project it straight upwards. Okay. The time for it to rise to its maximum height is 2.77 seconds. And its acceleration is this downwards. What is its initial speed? Alright. Pretty straightforward. So, this is number 10. And the lava bomb is in free fall. At the top, it will stop. Thus, we're going to be accelerating down at the grab field strength. That's probably about all I need for the watch. Right? Questions? Clarification? Alright. So, on to my how. So I'm going to grab my equation from my equation sheet because I want to know how it starts. I know lots of things about time and about position and things like that. So I'm going to use my standard one right here in the middle. Alright, see if I can use that one because that's kind of the one I want to use. So I'm going to start by writing that. Where I end up is where I start, how I'm moving when I start, and how much time I do that for. And 1/2 just to make the math people happy, how I'm accelerating, and how long I accelerate for. Right? And let me just check, what do they want to know? They want to know how high, or what's its initial speed. Oh, I'm not going to use this one then. I'm just going to use the other one from my equation sheet. The speed I end up at is the speed I start at, plus how I'm accelerating and how long I do that for. And I know when I get to the top, I'm going to be moving at 0 meters per second. I don't know what I start at. Hey, which direction do you guys want to call positive? Up? Okay. So I know because I'm in free fall, I'm accelerating downwards, and it tells me I'm at negative at that, and then it tells me how long I'm doing that for, which is 2.77 seconds.
In this, do we have to include saying that up is positive, or would it be assumed that up is positive unless said otherwise?
There, I've covered my bases. But
if we forget to add a number.
Yeah, as long as it's clear from here that you picked the direction. Because it really doesn't matter which way you pick positive, right? As long as you're consistent with it, then it's fine. Yeah, and just solve for V naught, the initial now. Because that's what it wants. Yay! Alright, so number 11, dropping a ruler. You catch the ruler 7.7 centimeters from the lower end. What is your reaction time? And we're going to assume that they started it as said in here. So we would go here, and we'd say it's number 11, and the ruler is in free fall, thus settle down at grav field strength starts from rest. Ah, that's horrible handwriting. I mean, those are the relevant points, right? So, start with our valid physics equation. I'm going to go back to my old favorite. Where I end up is where I start, plus how I was moving when I started, and how much time it takes, and how I was accelerating while I moved, and how much time it takes. Otherwise known as our general kinematics equation. Alright? So, I've got this ruler. Which direction do we want to call positive? Up? Okay. Where do we want to say 0 is? Alright, I'm going to say the bottom. Alright? So, that means I end up at 7.7 centimeters, which of course is 0.077 meters. Where I started was at 0 meters. How I was moving when I started, because it was dropped at 0 meters per second. I don't know the time. 1/2. I'm in free fall. That means I'm accelerating downwards at the gravitational field strength. Negative 9.81 meters per second squared. Negative because it's downwards. And delta t squared. And I love it when an equation has everything but one variable. Solve for delta t. That's your reaction time.
Well, there's also regular t. Like, is the...
T is t.
Well, there's a t and then there's a delta t.
No, there's a delta t and there's a delta t.
What about... Oh, t1/2 is it?
What? That's a plus.
That's a plus.
That's why I curved the bottom of my t's.
Never mind, okay.
For that exact reason. Alright, yeah. Alright, so number 12. Hot air balloon. What does ascending mean? Going up. Going up. So, we'll do green this time. Number 12. The camera is in free fall. Thus, settle down at grav field strength. The camera starts by moving upwards with the balloon. Free fall is accelerating down and starts by moving upward. You can even put in there, moves up, then stops, then moves down. That's what I put to the y. I'm going to sketch myself a little picture just so I have everything clear in my mind. So here's our handy dandy balloon basket with attached balloon. Here's our ground. They told us to use up as positive, right? Where do you want to set 0? Ground? Okay, so we'll set 0 down here, 0 meters. The path the camera follows actually goes up a little bit and then comes down. The acceleration is down the whole time, but my V initial would be upwards, right? Because it's already moving up. Because you're holding it in the balloon, and the balloon's moving up. If I just drop this right now, where is it going to hit? It's going to hit directly below it, right? From our perspective. But this table, if I was outside sitting in orbit, this table's moving at 1,000 miles an hour, right? Why is this hit directly on it? Because it's also moving 1,000 miles an hour with it, sideways. So the camera's in the frame of reference of the balloon. If the balloon's going up, the camera's going up from the Earth's frame of reference. But once it's dropped, it's still in the balloon's frame of reference, it's going to just straight drop. But we're in the Earth's frame of reference, where it's moving upwards, so it's going to keep going up until it stops, and then come back down. That's the universe. Stupid universe. What did we want to find? Time to reach the ground, and speed just before it lands. So, they want to know the time first. Let's do the time. So, I know, shocking. Right? And I'm ending up at the ground, so 0 meters. I started at, I think, 25 meters. Yep. My initial velocity was upwards at, mine was 7.9. So positive 7.9 meters per second. Delta T plus 1/2 negative 9.81 meters per second squared, because I'm assuming this is happening on the Earth, right? Delta T squared. Solve for delta T. Some of you might want to use like the quadratic solver in your calculator or Wolfram or something, you know. But I'm confident you guys can solve that quadratic for delta T. Then the second question was, how fast is it moving just before it hits the ground? For that, I can do that one of two ways. I can do that using the time, or I could do it using the displacement. Now, if I did my time correctly and I know it's correct, that's kind of the more straightforward way to do it. If I think I may have screwed up my time, I'm going to do it without using time just so I can be sure of that. So if I go back to my equation sheet, which is here, I've got these two equations grouped over here, which both talk about your velocity changing, one because you're accelerating for a certain amount of time, that's the top one, and the bottom one because you're accelerating for a certain displacement. Remember, delta D is displacement. So I'm going to actually, I could use that top one as long as I'm sure my time is right. I'm going to use the bottom one because I haven't checked my time, because I'm trying to move quick. So I'm going to use that V final squared equals V initial squared plus 2 alpha, or sorry, 2a delta D. And so, now the only thing I have to keep in mind is which direction is it going to be moving when it lands? Down. So I want, my answer here is going to be positive, because that's the way the squares work, right? But I bet they want a negative answer in there. That's why they're saying up is positive. I bet that's what they want. So here I'm just going to substitute in. I don't know my V final. My V initial is at positive 7.9 meters per second. Plus 2. I've got negative 9.81 meters per second squared. And my delta D, so that's where I start compared to where I finish. Right? Delta is always final minus initial. So where do I end up? On height. 0. Minus where I started, which was 25. And the negatives take care of each other. They're good that way. So a lot of people will get an answer and they'll forget that they solved for V squared when you want V. So don't forget that final step of square rooting. Alright, so 15. You've got someone standing on a scale. Oh, what does the scale measure? Normal force. Scale reads 745 newtons of normal force. During the storm, the crew member observed a maximum reading of 905 newtons normal force and a minimum reading of 550 newtons of normal force. Find the upward max acceleration up. Find the max downwards acceleration. All right, so this was one of them that you needed a force diagram for. So I'm going to need 3 diagrams. Accelerating up, not accelerating, and accelerating downwards. Although they'll be very similar. So I'm going to have the scale, and I'm going to have the person 3 times. It's a big old scale. Alright, so this one will have acceleration up, that one acceleration 0, this one acceleration down. Now what's constant in all these cases is the gravitational force, right? Because we're not changing planets, we're not hacking off the guy's arm, or something like that. The gravitational force now is constant, right? But what changes is the normal force. In this case, I know it's going to equal the gravitational force. Here, it's got to be bigger because I need a net force up, and here it's going to be smaller because I need a net force down. That would be your whole Y right there. Maybe if you really wanted like those brownie points, you'd put scales, measure, normal force. And that would be like, oh man, even though he made a little mistake, he still gets a 10 out of, she still gets a 10 out of 10. That brilliant insight there. Good? All right. The equation from our equation sheet here is forces again. We're going to do the sum of the forces equals mass times acceleration. Newton's second law there. And they really only wanted me to do it before and after, right? So they only care about maximum upward acceleration and maximum downwards. So the upwards is going to be when the 905 happens, and the downwards is going to be when the 550 happens. And in the middle, we'd have the 745. So that middle one is telling me, in my drawings, the middle one, the non-acceleration one, is telling me the value of f sub g. Kind of clever there. So we'll do accel up, accel down. Give me some page. So some of the forces in the y equals MAY, just to make sure that I'm thinking in the y direction. Do we want to just go with the convention of up is positive? Okay. So if we go with the convention of up is positive, we had a positive force normal minus an f sub g equals m times a positive a. And over here we had a positive force normal minus f sub g equals m times a negative a. Oh, we kind of have to do the center one, don't we? We're going to, though, because they don't tell me the mass. Positive force normal minus f sub g equals 0. Right? But it's not accelerating. So force normal equals f sub g. And I look on my equation sheet and realize, oh, f sub g is mg. Right? That handy dandy equation sheet there. So 745 newtons equals m, and I'm on the surface of the planet, so 9.81 newtons per kilogram. And I find out my value for m. Which for me is 75.9429 kilograms. Over here, I have, what was that, it was 9 something, right? 905. 905 newtons minus 745 newtons equals 75.94 kilograms times A. Solve for A. Over here I have 550 newtons minus 745 newtons equals 75.94 kilograms times negative A. Solve for A. So I needed that m to be able to solve for them. That's why I had to do that third part. All right, so we're going to do 18 here real quick. Nice cube, microwave oven. This amount of power takes this many joules to melt it. How long does it take the ice cream to melt? Oh, okay. Good, this is a different type. So, 18. Power is the rate energy is used by something. And you could expand on that. I'm going to skip over expanding just because of time and saying things like, power, the more power, the faster energy is used, the longer you use the same amount of power, the more energy. So you could expand on that. Probably one more sentence would be good there. But I'm going to just for time, I'm looking here at power, and I'm going to use the form that power equals change in energy over change in time. So power equals change in energy over change in time. And now I'm just plugging in. 115 watts, that would be the power, equals 30,200 joules. 30,200 joules, delta time, solve for delta time. And that would end up being in seconds. Because a watt is a joule per second. Yay!
So